Welcome to my channel. I know you've been waiting. Today we'll be continuing our considerations about Green's theorem, and I hope we'll end the preliminary stuff today, and we will start the proof itself probably in the next video. So, as you may remember, we have shown that we can decompose any open set into not simply, but connected domains. So this was the previous theorem that we have proven. And what's more, this is the information that we needed in order to establish the fact that we can consider our, for example, differential equations and such things separately on each connected set. So basically we can restrict ourselves to work on connected sets. So this is plenty of simplification because how to say it, open sets can behave very wildly, but now we are in the family of connected sets, so this is something that is easier to handle. But we finished just before the proof of the fact that any 2 points of any domain can be connected by piecewise C1 curve. So that's why we needed this, say, little lemma. I mean, it's not really a lemma, it's just the fact that we can obtain very easily that if we have connected set, then any sets that are simultaneously open and closed are the X itself. So only the whole set can be both open and closed. So this is what we have proven in the previous video. If you want reference, please go check it. And now we are heading to our theorem that I've been talking about. So this is stated as follows: if we take any domain D on R2, then D is piecewise C1 path connected. So any 2 points can be connected by piecewise C1 curve. And this is proven using this lemma that I mentioned. So basically, we argue as follows. So let D0 be set of all points that are connectable by some piecewise C1 curve in D. And we will show that this set is both open and closed. One more thing, okay. I forgot in the proof of the previous lemma that it has to be, of course, non-empty set, because empty set is also both open and closed. So this was the fact about non-empty sets. So this is important, but we know that D0 will be non-empty because we can always choose a point, just one point, any specific point like P from D, and then P can be connected by a constant curve in D, so there is no problem. It is always non-empty. So let's now show openness. So this is proven basically on the same line as we argued before in the proof of previous theorem. Namely, if we take any point, we want to show that the ball of radius, say epsilon, can be fit inside D0. So basically we need to show that if we choose sufficiently small ball, all points from this ball can be connected by some piecewise C1 curve. So that's our reasoning. And this is easy because we know that we can connect any point from D0, we can connect it with P0 through some piecewise C1 curve. And any point from any point from the ball can be connected with P0 by just straight line segment. So this is then we just obtain piecewise C1 curve because we append it in one point, this say primary curve, we just append it by the line segment. We make a junction in one point, and this is the only point where the differentiability can break because there are no other singularities. I mean, maybe these words like don't describe it that well, that this is very rigorous, but I mean, it is easy because we just make like appended function uh, from say a to b as this C1 curve, and then maybe from b to b plus 1 we make this straight line segment. So this is piecewise C1 on both AB and B to B1, and this one point may possibly be the curve may be not differentiable, but this is not problem for us because it's only piecewise differentiability, so there is no problem. And this fact gives us the fact that any point from the ball can be connected to any point from D0. So we basically we have shown that this is open set. So now let's deal with closedness. So how do we argue? We will use this sequential definition of closedness. I mean, this is equivalent for sure in R2 to the standard one. So let's do it. So let's choose any sequence Pn from D0 that is convergent to some P from D. So we basically don't consider sequences that are going outside, I mean, that the limit is outside of D, which can happen because D is open in R2, so it certainly may not have limit in D, since in particular it is not complete. So okay, but now we can take our P and choose some epsilon such that ball of radius epsilon centered at P fits in D. So we just want to have ball that is solely inside D. But now we know that there exists some capital N such that for n's bigger than this capital N, since Pn is convergent to P, we need to have Pn's in this ball for n bigger than capital N. So this is just basic convergence. Okay, but now we can connect any point from D0 to Pn and then have a straight line segment to P. So once again, from this like local arcwise connectedness, I mean from the fact that it's even stronger that we can locally always connect anything from the ball with center through straight line segment. From this fact, we obtain that P has to be inside D0. So that's basically what it means for D0 to be closed. So we basically shown that D0 has to be the whole set D, the whole domain D, like to sum up. And this fact gives us that any 2 points from the domain D can be connected by piecewise C1 curve. So this is something that we wanted because now it will be for sure easier for us to define functions through integrations on some curves, because we know that if we have domain, we can connect any 2 points by such curve, and that any open set can be decomposed into domains. So we are one step ahead in proving, or maybe in constructing potential for our integrals of motions, which I remind was our like primary problem. Okay, so let's maybe focus a bit on this problem. So as I said, we have decomposition into some nicely behaved sets, and now we know, I mean, we can argue in the following way. If we have some function f that is twice differentiable in continuous manner, on set U of course, then if we choose any curve that goes from say A to, I mean, from some point P to some point Q, then we know that for any t from this interval a to b, f of gamma of t is equal to f of gamma of a, of the starting point, f of the starting point, plus the integral over from a to t over t prime of f composed with gamma. So this is just the fundamental theorem of calculus. So this is what it is. And now, from the fact that f is twice differentiable, and gamma is of course piecewise C1, we know that this derivative is equal to gradient of f, scalar product with gamma dot. So gamma dot is just the derivative of gamma, of course. And this equality holds almost everywhere. So I mean, this is maybe not that properly said, because maybe the better way of understanding is that when gamma is differentiable, I mean for t such that gamma is differentiable, this equality holds. So basically, we have to keep in mind that when we write down this derivative, we just kind of want to express the fact that it is almost everywhere true, namely that the integral doesn't see the difference. Maybe if someone is very curious, then one might look up the definition of absolute continuity, uh, because for absolutely continuous functions, this Lebesgue version of fundamental theorem of calculus works. And here we are actually working with absolutely continuous functions, so there is no problem. Okay, but I don't mean to spend that much time on that. If someone was curious about the details of this, please write me down in the comment, so maybe I will do video on this. But right now we are moving to next thing. So okay, so we know that if function is as such and curve is as such, then this equality holds, this equality regarding the gradient and the derivative and the integral. So we know how to write down the function in terms of function at some point and integral of derivative of this function through the curve. So one might ask if, I mean, trying to do it other way around, is it possible to choose any vector field, integrate it over some curve, hence any curve? I mean, this hence is to be shown or to be disproven, but we are asking if such procedure give well-defined function. Okay, but for that to be true, we would have to prove that if we integrate this vector field over any two curves starting and connecting the same point, this would have to be equal in order to have even well definiteness of the function, because if we define the function as integral from one point to another, then we need to have that this is independent of path, because function can have only one value in any point. So this would be the problem if it wasn't. And first thing to notice is that if we just play a little bit with parameterization, then we can see that if we have integral over gamma 1 and integral over gamma 2 subtracted, then this is basically loosely saying equivalent to the integral over the closed loop. So it is sufficient to check only closed loops. I mean that integrals over closed loops of such vector field is equal to 0. And on the other hand, if we have this integral over loop is equal to 0, then the function is well defined, because we know that if we choose any curve to integrate over, we know that any point can be obtained by some curve. So basically we just have to choose some curve from, say, x0 to x, I mean x0, y0 to x0 to xy, integrate over this curve, and this gives us the value of our function. So since this does not depend on gamma, then any point has only one value, and the function is thus well defined. And this is summed up in my notes, namely that if we choose any constant and define the function as c plus this integral over vector field dot product with gamma dot is well-defined function. Of course, only on one domain, because as I said before, we are restricting ourselves to working only on domains. Because if we have open set, like general open set, it is composed of domains, so we can just solve the same problem separately on each of these domains and just glue up the result. So basically, in order to produce function, we have to choose some point P, some vector field such that integral over closed loops are zero, and some constant C. This is again like gauging the potential. This constant is meant to do this. Then we can construct function as noted above, of course with gamma A equal to P in this notation. But for any like really existing function, there are multiple ways to obtain any function in such procedure. Namely, we have freedom of choosing the starting point D, because like if we choose some point, the gradient as the vector field and constant as f of x0, y0, then it will always gives us this procedure will always give us in return this function, this exact function was used to define this triple. Okay, and for us, like for generalities, not of much relevance because it's appendix to the videos on physics that I make. So we'll choose the function f to be of class C2 on the open set, so that the gradient is of class C1, which makes us check only once differentiable fields to the once differentiable vector fields on closed loops. I mean, we'll be just checking this for C1 vector fields. Okay, so we know what task is in front of us. We need to somehow characterize characterize integrals over loops of vector fields of class C1. And this will be done in next video, where we'll start finally proof of the Green's theorem. So that's what in front of us. So stay tuned and see you in next video.